You're watching a Channel 98 NBISD TV production.
Welcome to another edition of That Geometry Show. I'm your host, Kevin Corpy, and if you're a faithful viewer or you're just tuning in for the first time because you happen to be flipping channels and you're on your way to Channel 100 and you saw these cool graphics, I invite you to stay, roll up your sleeves. You can download the worksheets I'm going to be using today from the district website at www.newbraunfels.txed.net. Grab a sharp pencil or a dull pencil and sharpen it. I'll wait for you. Okay, not for long. And then come right back and we will do some geometry together. Today is Lesson 20, big show, big number. We're a tenth of the way to our 200th episode, so we're getting close. All right, Lesson 2.0, the big 2.0. This is going to go along very nicely with the two sections in your geometry textbook, 7.4 and 7.5, parallel lines and proportional parts. We've been dealing with proportionality for a couple weeks. We've talked about parallel lines in the past. Today we're going to put both of those together. Okay, now in mathematics, theorems are very, very important. And this episode really could be called the theorem episode because there's lots of theorems. Now, theorems that have names like 7.1 and 7.2 are important. But the really important theorems are the ones that have their own special name, like this one here, the triangle proportionality theorem. If it has its own special name, you could be assured that you're going to be responsible for knowing it. Not only its implications, but how to work with it, okay? Now, a lot of the theorems on today's shows are application theorems, which means you're probably not going to have to use these in a proof, but you're going to have to use them to solve problems. Okay, let's get to the first theorem of many on today's episode. It is called the triangle proportionality theorem, and here's what it says. It says, if a line is parallel to one side of a triangle and it happens to intersect the other two sides at two distinct points, then, the conclusion says, it will separate the two sides that it intersects into segments that are proportional to each other. Okay? Now, that's a lot of words, and I have a diagram to go along with what that means, but it also works in reverse. And if you remember from a previous episode, that means the converse is true. So if we happen to have a line that divides the two sides proportionally, it will be parallel to the third side. Okay? This is actually an if and only if statement. Now, let's look at a little closer diagram to see what that means. All right, putting that theorem into the context on a diagram here. We have a triangle ABC, and we're given that segment DE is parallel to AC. And you can tell that's the symbol for parallel. We can also tell from the diagram because it has the two arrows on it. So these are parallel lines. Well, what the theorem tells us then is that segment DA, this one here, is to segment BD, as segment EC, this one here, is to segment BE. So this line, it intersects these two segments, these two sides. It's parallel to the third. It will divide these two lines up proportionally. Now, we don't have to go DA to BD. We can set proportions up a couple of different ways, as long as we are setting up the corresponding sides. We could have equivalently have set it up, DA is not to BD, but the corresponding part on the other side to DA would be EC. So we could say DA is to EC as, same thing over here, BD is to BE. And if we set it up like that, that's going to be fine. If we cross multiply, the cross products in either one of the two proportions will be equivalent. Okay? The important thing to remember again is when you're setting up a ratio, there's going to be more than one way. You must set it up to the corresponding side lengths. All right? Now, this theorem is probably ringing a bell in your head because we did look at it last week when we talked about solving similar triangles. It was that third kind of bonus way to do it that made the math a little bit easier. But today we're going to look at it a little more in depth, a little more in detail, and to do that we have an example here. So, based on this figure, it's triangle ABC, and we have this other triangle ADE that's embedded inside of it. Notice these two triangles, the large one and the small one, share a common angle A. We want to know which of these statements here is false. So we're looking for the one that is not true. Well, let's go ahead and go through and analyze each one and decide if it's true or false. The first one says segment DE, which is this one, is it congruent, or parallel, sorry, is it parallel to segment BC? Well, from the diagram, they sure appear to be parallel, right? But there's no marks indicating that they are. If they had arrows on it, it would be a foregone conclusion. So you can't just assume that they're parallel if there's nothing there to tell you that. So how are we going to figure that out? Well, remember the theorem I just told you about works in reverse. It's basically saying if the sides that this line DE segment divides up into proportional parts, then DE will be parallel to BC. So we just have to check for proportionality. So we could do it a number of ways. We could say AD, which is 3, is proportional to DB, which is 3. Is that equal to, the corresponding side would be AE, which is 4, is to EC, which is 4. And well, let's see. If we simplify, 3 over 3 is 1. And yes, in fact, that is equal to 4 over 4, which is 1. Okay, now the other way we could have set it up just to show you is we could have gone AD is to AE. So we would have gone 3 is to 4, question mark, as this DB, 3 is to 4. And those don't simplify, but notice we still get a true statement. 3/4 is equal to 3/4. So in both cases, we set up the proportion two different ways, each time, though, according to the corresponding sides, and we got true statements. So by the theorem, we now know that segment DE and BC are actually parallel. So that's a true statement. Let's move on to the next one, choice B. It says triangle ABC, the big one. Remember, this little tilde means similar to triangle ADE. Remember, similar triangles have corresponding angles that are congruent. Well, it's helpful now that we know that DE and BC are parallel, because I can extend this parallel line and this parallel line, and now I can look at segment AB or DB to be a transversal, so that this angle here and this angle here are congruent. From a previous episode, we talked about those. Those are corresponding angles. If I look at this line being a transversal to those two parallel lines, angle DEA and angle BCE are also corresponding angles. They are congruent. And of course, angle A will be congruent to itself. That's the shared angle. So because all three angles that correspond to each other are congruent, we can say that the triangles are similar to each other. All right? So far the first two are true, so hopefully one of these last two is false. Part C, triangle ABC, that's the large one again, is congruent to. The little tilde with an equal sign underneath means congruent to. Triangle ADE. Remember, congruence means not only are all the angles congruent, which we've already established, but all the side lengths are congruent as well. It not only has to be the same shape, it has to be the same size. Well, clearly you could see that this triangle here, it's contained inside the larger, so it can't be the same size. Or you can think about it this way. This side length of the small one is 3. The corresponding side on the big one is 3 plus 3, or 6. So they're not congruent. The side lengths are different. Well, let's look at choice D. It has to be true now, right? D is the midpoint of segment AB. Well, here's A, here's B. So this is the segment AB. We're asking if D is halfway in between there. Well, if we're given that the measure of segment AD is 3 units, and the measure of segment DB is also 3 units, since they're the same measure, D would have to lie right in the middle, making it the midpoint. So yes, it's also true. And again, if you have time, even though you found your correct answer, it is helpful to just verify that the last one is true. Who knows? Everyone's capable of making a careless mistake, and that way you might catch it. All right, now that last example leads us very nicely into another important theorem. Okay, here it is. It says a segment whose endpoints happen to be the midpoints of the two sides of the triangle, just like the one we worked, well, then we know that that segment is parallel to the third side of the triangle. Well, we kind of verified that in the last example. Well, this theorem tells us now that if we know that it bisects the two sides, we don't have to test to see if it's parallel anymore by setting up the proportions. The theorem tells us that it automatically is. But this theorem has a little bonus piece of information, and it tells us that the length of that midpoint segment is 1/2, or half the length of the third side. That's a good little piece of information. These are application theorems. Let's apply that information to the following example. Here we go. In this triangle, we want to find the value of x. How many times in math class have you been asked to solve or find x? Okay, it's very important. You think by now we would have found it, right? Well, that's the thing. X is a variable, so from problem to problem it does vary. We have to find it each time. All right, well, let's look at it. we have one triangle and another one contained inside of it. These marks, remember, mean that this segment is congruent to this segment, and this segment is congruent to that segment. Well, what does our theorem tell us then? It says if a line segment like this one here bisects the two sides, and we know it bisects because they're equal length, then this side is parallel to the third side, that it's not intersecting. So by the theorem, without setting up any proportions, we know that this is parallel to that. So we can draw the arrows to denote that. Well, the other part of the theorem is going to help us find x. It says now that we know they're parallel, this line segment here is 1/2 the length of this side. So again, because we know that this segment bisects the two sides here, by the theorem, we know that its length is half of this. So again, one of the hardest things in mathematics is to take a verbal sentence like this segment is 1/2 the length of this one and translate it into a mathematical equation, which is basically a sentence. So I'm going to go ahead and reread it, and as I do, I'm going to show you how to set it up. It says that the segment that intersects the two sides, its length, which is 2x plus 5, so I'm going to write that down, is. Okay, now that's a verb. In mathematics, the is the equal sign. Okay, so this side length is equals 1/2, I'm going to write the 1/2, the length of the other side, which is 6x minus 14. So the of is basically multiplying. So that wasn't so bad, but now that we have an algebraic equation with one variable x, we can solve. So I'm going to go ahead and leave the left side alone. I'll distribute the 1/2. 1/2 times 6 is half of 6. And I get 3x minus half of 14 is 7. And we'll collect our x's on the left. So if I subtract 3x, 2x minus 3x is negative x, which means I have to subtract 5 to get it over here. And I get negative 7 minus 5 is negative 12. Now I can divide both sides by negative 1 or multiply both sides by negative 1. And if I do that, I get x is 12. Okay, so we solve for x. Let's go ahead and verify if we have time. By plugging a 12 back into here, I get 6 times 12, which is 72, minus 14, which gives us this length to be equal to 58. And again, if I plug the 12 into the other length, 12 times 2 is 24, plus 5 is 29. Now we can quickly check. Is 29 half of 58? Yes. Is 58 twice of 29? It sure is. Okay? So that's an application theorem. We use the information to help us solve for x. And we had time, so we checked it. Now, are you ready for another theorem? That's a silly question, right? Why else would you be watching the show? Let's get to one. Another theorem. Here we go. If 3 or more parallel lines intersect two transversals, then they cut off the transversals proportionally. Say what? It's not even time for that portion. Okay, did that make sense to you? Well, again, a diagram will help illustrate it. We have 3 or more parallel lines. So in this diagram down here, I have 3, and I know they're parallel because I have the arrow on them. They're intersecting two transversals. These are transversals. They're just coming in at an angle to the parallels. They cut off the transversals proportionally. So what that's going to mean in the context of this problem is segment AB is going to be proportional to segment DE, this one up here, and that's going to be the same proportion as BC is to segment EF. So notice I set it up. I said AB is to DE, so this one is to that, as this one is to that. Well, you can set it up alternatively by saying segment AB, and you can stay on the same side. AB is to BC, as. Now if I went from left to right up here, I'm going to have to go from left to right up here to stay corresponding, as DE is to EF. And again, as long as you're setting up with corresponding sides, your cross products are going to be equivalent, and you're good to go. So let's go ahead and set up this proportion. What do we know? We know AD and BE and CF are all parallel. Okay, it's given up here with the symbols. It's given here with the arrows. We know that the measure of AB is 4 units. I'm going to go ahead and label that as 4. I know the segment DE is x plus 1. There's that x. BC is 6 units, and EF is 3x minus 9. So I have 2 numbers and 2 variable quantities here. I want to solve again for x. Surprise! Well, how are we going to do that? We could pick either one of these proportions. Now, what I'm going to do, since I notice I have 2 numbers on the bottom, and they're both divisible by 2, and this is just an advanced strategy, to make the math a little bit easier, I'm going to set it up like I did over here the second way. So I'm going to say 4, this is to 6, as, going up here, x plus 1 is to 3x minus 9. So I'm going from left to right. Now the reason I did that is because I can simplify 4 6. 2 goes into 4 twice, goes into 6 3 times. So we're essentially dividing out of 2. And I do that before I cross multiply just to make my numbers a little smaller. Now I can cross multiply, and I'm going to wrap around down here. So 2 times 3x minus 9 equals 3 times x plus 1. So those are called the cross products, remember? And now we just simplify. So I'll distribute, and I get 6x minus 18 equals 3x plus 3. And then I'll wrap around down here again. I'll collect my x's on one side. So I get 6 minus 3 is 3x. Bring the 18 to the other side. 18 plus 3 is 21. And finally, dividing both sides by 3, I get x equals 7. And if you have a chance to check, plug it back in. 7 plus 1, that means that DE ended up being 8 units. Plugging in a 7, I get 21 minus 9, which is 12 units. So notice, from AB to BC, 4 to 6, it's really times 1.5. This is 1.5 times larger than 4. And notice to go from 8 to 12, 12 is 1.5 times larger than 8. So they have the same ratio of proportionality, okay? And we could expect that. Time for a short break, but do not go away. We'll be right here waiting for you when you get back.
Bad people, the gang members in the neighborhood. My brother, he wouldn't be happy at all if I was to tell him I was going to drop out of school. He would not approve of that, because then that's going to be 2 of us not handling our business.
Me and my friends are close, and we all believe in each other. I know they could graduate, even if it takes them longer than the 4 years.
We have classes together, so
we study together, we help each other with our homework.
Realized we messed up in the past.
Failed a couple classes before, not doing as much work as I should be doing. My 2 best friends, they keep me working hard.
So you used to be taller. What happened?
What happened? Pressure. The pressure to be so cool and so popular and to never say the wrong thing to anyone, so I'm cool with everyone. The pressure to drink and get high. Pressure happened.
So now what?
I don't know, but this isn't working.
All right, welcome back to that geometry show. Let's get right back to the math. Okay, now before we move on to some really important theorems, it's time to look at another theorem, okay? Now remember, the theorems that have their own special name are really, really important theorems, as opposed to just really important theorems. They have 2 reallys in front of them. This one does have its own name. It's called the angle bisector theorem. And we've looked at angle bisectors on a previous episode. Now we're going to look at an implication inside of a triangle. Here's what it says. An angle bisector in a triangle divides the opposite side into segments that have the same ratio as the other 2 adjacent sides. Reread. That's not part of the theorem, but it's an instruction. An angle bisector in a triangle, okay, that's down here. So CD is our angle bisector, which means this angle and this angle are congruent. I'll put the tick marks there. It divides the opposite side into segments that have the same ratio as the other 2 adjacent sides. Well, that's pretty cool. Here's what it says. It says that segment AD, right here, is proportional to segment BD, the other side on the base. As, well, if I started with this portion, I have to stay on this side. So as CA is to CB. So this is to this as this is to that. Left is to right as left is to right. Or, if you prefer to set it up, you could stay on the left side. AD is to AC, as, now jump to the right, as DB is to CB. Okay, so left is to left as right is to right. Again, as long as you're setting it up with the corresponding sides and you make your C's legible so your teacher can read it, your cross products are going to be equal. Okay? So, pretty important theorem. We talked about angle bisectors before, but now we talked about proportionality. It's an application theorem, so guess what comes next? The application. That's right. In this example, we want to find the value of x. Imagine that. Same old thing. Solve for x. Well, notice we have a triangle, and these red marks here indicate, without saying so, that these 2 angles are equal. So this line segment here, which isn't even labeled, must be an angle in bisector. It bisects this larger angle. We know that the length of the entire base is 19, and this little segment here is x. We want to solve for x. Well, I'm going to go ahead and give this quantity right here a label. If the whole thing is 19 and the little piece is x, this must be what's left over from 19, or 19 minus x. Labeling it in terms of the variables that are already there and the number that's there is better than introducing another variable instead of just calling it y. All right, now let's see if we can use the angle bisector theorem to solve this. I can set it up. I could say x is to 8. So I'm staying on the left side. X is to 8 as 19 minus x is to 14. Now notice the way I set it up, we can't really simplify either one of the two sides, so we're just going to go ahead and jump right in and cross multiply. So I get 14x equals 8 times 19 minus x. And here's where your calculator might help you. 8 times 19 is not too bad. It is 152 minus 8x. And now I'll add 8 to both sides, and I get 22x equals 152. And then divide both sides by 22, you get 152 20-seconds, which actually simplifies, if you divide out a 2, to 76 elevenths. And if you have your calculator, you can punch that in, and it's about 6.9. So we have our answer. Now there's another way we could have set that up. I will set it up, but I won't solve it. We could have set it up as x is to 19 minus x, left to right, as 8 is to 14. We would have gotten the same answer, and in this case we could have simplified 8/14 before we cross multiplied. So I'll let you try that one on your own, and give me an email if you have any problems with it. All right, one last application, and then I can hardly wait, my favorite part of the program. In the figure below, which happens to be a triangle, segment RU bisects angle TRS, So in this case, we're not given the marks indicating that it's a bisector. They're telling us. So I'm going to go ahead and draw my little tick marks, angle tick marks there. We want to find the value of y. Well, this problem is really no different from this one, except just to change things up, because you're probably tired of solving for x, we're going to solve for y. It's a variable, so a variable can be anything, including another letter. So let's call x y. So let's go ahead and set it up. We did set this one up going left to left, right to right. So let's go ahead and set this one up the other way. We'll go left is to right, so y is to 7.2. As left is 2 is to 8. And in this case, I can simplify. So I get y is to 7.2 as 2/8, which is 1/4. Now I'll cross multiply, and I get 4y equals 7.2 times 1, which is 7.2. Dividing by 4, I get y equals 7.2 divided by 4. Now, a word about this. This is mixed notation. A decimal represents a part of a number, and so does a fraction. I don't know if your teacher will allow you to keep an answer like that, but I'd prefer it not. It's like speaking two different languages. So you can either put it entirely as a fraction or entirely as a decimal. Your calculator will help you do this. 7.2 divided by 4 is 1.8, which on your calculator, if you have a TI-83, you can hit math, enter, enter. Most of y'all know that, and it'll convert it to you to 9/5. Or you can call 1.8 1 8/10, which is 4/5, and convert the mixed number, which is a much more invigorating intellectual exercise. Either way, though, you get 9/5. Now it's time for Say What? Okay, my favorite part of the show. Well, instead of an application today, remember I said we were going to talk about a lot more theorems? Well, there's a lot more theorems, okay? And some of you might know this, some of you might not. But if you have two similar triangles, not only are the sides proportional to each other, and everything else that we've been looking at is proportional, but there's special quantities and special parts that we've looked at in a previous episode that are also proportional to the corresponding sides. Say what, right? What does that mean? Okay, that's a lot of information, a lot of words. Again, let me explain with some helpful diagrams here. So here's exactly what I mean. If we have two similar triangles, all these examples, I'm going to presuppose that the two triangles drawn are similar. So I'm not going to try and prove that or verify that every time. Just go with it. They're similar. Okay, so I've labeled, for convenience, the side lengths instead of labeling the vertices. So I have side A, side B, side C, and it corresponds to side D, side E, and side F. Okay, so they are similar. If they are similar, we know that their perimeters are also proportional to the corresponding sides. That's pretty cool. Well, the perimeter is just the distance you would walk if you strolled all the way around. So what we can say then is the perimeter of the first, A plus B plus C, is to the perimeter of the other, which I'll do it in the corresponding order. D plus E plus f, the ratio of their perimeters is equal to the ratio of the corresponding sides. Which sides, you say? All of the ratios. So A to D, A corresponds to D, B corresponds to E, and C corresponds to F. That's pretty cool, okay? And it does make sense if you think about it, so let's think about it. Let's say that this triangle happened to be twice as large as this one. That means every length was twice as big on this one as this one. Would it make sense then if you were walking around the larger that you would have to walk twice as far as you would if you had to walk around the smaller one? It should make sense, okay? It's because a perimeter is a linear quantity. And we're going to talk about area on a later episode. And this is not really true of the area because the area is a squared quantity. But for perimeter, it works, all right? Here's another thing from a previous episode. The altitudes are proportional. Remember, an altitude is something that's dropped from a vertex that's perpendicular to the opposite side. So I'm going to call my altitudes h and y. They are also proportional to the corresponding sides. So let's go ahead and take a look at what I mean here. I'll say h is to y, this altitude is to that altitude, as the corresponding sides. A is to D, as B is to E. And I didn't label the other sides because I thought it would clutter up the diagrams, but I'll do so now. If I called this C and I called this F, then the ratio of the altitudes is also proportional to these other sides. Now notice I'm going small triangle in the numerator, large triangle in the denominator. Again, that's the corresponding part that's so important for a ratio. We also know that in two similar triangles, the angle bisectors are proportional. Well, an angle bisector we've already seen today. It's dropped from one vertex and it bisects the angle. It doesn't necessarily have to be perpendicular, or it doesn't have to really bisect the opposite sides. It just bisects the angles. Well, I'm going to call the small one h and the large one y. Now, I've been going small to large, and that's okay. But did you know you can go from large to small so long as you keep the correspondence the same? So I could say the angle bisector of the large, which is y, is to the angle bisector of the small h, as D is to its corresponding side A, as E is to its corresponding side B, and what the heck, I'll label this side F again and this side C, as F is to C. So large is to small, as large is to small. And the last one here, the medians are proportional. So let's review a median. A median is also dropped from one side, one vertex, but it's dropped in such a way that when it lands on the opposite side, it cuts that side in half. It bisects it. Okay, so I've denoted that with the two congruent marks here. So I'm calling them h and y. And I prefer to go left from right, although up here we went right to left. So small to large, I'll say h, the median of the first, is to y, the median of the second, or the large. And that's proportional to the corresponding sides. So again, this seems repetitive, and that's because it is. A is to D, as B is to E. And again, just to be consistent, we'll call that F. This is side C, as C is to F. All right? Now you know, okay? A lot of theorems today. You know them all now, so go out and use your new power wisely. All right, that concludes today's episode. Notice there were a lot of theorems that we covered today, and the best way that you can help yourself be successful with working with those theorems is to sit down and memorize them before you begin practicing with the exercises. As you're working the exercises, try and make sense of what's given, what you need to find, and which theorem applies. Looking it up, of course, if you get which one applies, okay? But you're only going to get good with practice, and you're only going to make the most out of your practice if you have the theorems memorized beforehand. If you have any questions at all while you're working through any of these problems or anything in class, please feel free to send me an email, and I'll return it as soon as I can. It's kcorpy@newbraunfels.txed.net. Well, we're out of time, so until next time, I'm Kevin Corpy, and I will catch you on the flip side.